Lecture 28, Transition Metals and Transition Metal Complexes. Transition metals are the B group elements in the middle of the periodic table that provide a transition between the properties of the leftmost metal elements and the rightmost non-metal elements. These elements have very similar electronic structures in that they have valence electrons both in s and d orbitals. Typically, the valence electrons are in the ns and n-1d or subshells, where n is the row number for the elements. This has many consequences in the chemistry of these elements. For starters, you see a variety of oxidation states for the transition metals. This is unlike the main group metals and non-metals, well, mostly metals, where those metals have usually one or two main oxidation states. As you can see in this table of common oxidation state for the first row of transition metals, scandium through zinc, there's a variety of oxidation states available to transition metals. You can also see that the number of oxidation states is greatest for elements within the middle of the block of transition metal elements. This is because the elements that are on the outskirts typically behave more like main group elements. A good example of this is zinc, which only shows a +2 oxidation state, because the electronic structure is very similar to that of the group 2A metals. The oxidation states that are highlighted in green are the most common oxidation states observed for each element. You'll notice that most of the transition metals in the first row have an oxidation state of +2, or can have an oxidation state of +2. This is because all transition metals have one or two s electrons. The s electrons are on the outermost part of the transition metal atoms and are usually ionized first, since they are furthest away from the nucleus on average. This is why most transition metals do have a +2 oxidation state. One important skill that you might want to review from Gen Chem 1 is how to write electron configurations for the transition metal elements and ions. We'll practice this now by writing electron configurations for manganese 4+ and cobalt 2+. We'll stick to writing electron configurations using noble gas notation, since we're mainly interested in the valence electrons outside of this noble gas core of electrons. The way that I like to think about writing electron configurations for metal ions is to think about what the electron configuration is of the neutral atom first, and then subtracting the appropriate electrons. For manganese, which is in the first row of the transition metals, we can write an electron configuration by finding the noble gas immediately before that element. For manganese, that's argon. So we put argon in square brackets. Then we count the electrons. We count in the elements on the periodic table that correspond to different subshells. Since manganese is in the fourth row of the periodic table, we start with 4s. We have to go through both of the s block elements in the fourth row to get to manganese. Therefore, we count 4s2 first. Then we need to go into the d block. Remember that electrons fill the n-d subshell, where n is the row number. Since manganese is in the fourth row, this means that we're filling a 3d subshell. We need to count 5 elements in to get to manganese. This gives us 3d5. Therefore, the complete electron configuration for manganese is argon 4s2 and 3d5. Now we're ready to make ions. As it says on the left, the s electrons are usually the first to be ionized away from an atom. Therefore, when taking away electrons from d elements, we want to remove the 4s electrons, or the s electrons, before we start removing d electrons. Therefore, to make manganese 4+, we need to remove the 4s electrons, followed by 2 of the 3d electrons. This gives us a final electron configuration for manganese 4+ as argon 3d3. We do something similar for cobalt 2+. We can write an electron configuration for cobalt, which is argon 4s2 and 3d7, and then remove 2 electrons to get the final electron configuration. The 2 electrons that we'll remove are the 4s electrons in this case, leaving us with argon 3d7. As I mentioned before, you should probably review material from Gen Chem 1 that help you practice writing electron configurations for transition metals. We're now ready to take a look at some of the periodic properties of transition metals. You might remember that I said several times that many periodic properties such as ionization energy, electronegativity, and atomic radius tend to only show the trends that we've discussed earlier for main group elements. Transition metals, on the other hand, tend to show periodic properties that are quite different. Let's first look at transition metals as we go across a row. It turns out there's very little variation in periodic properties as we go from left to right across a row of transition metals. This is due to the little variation in the effective nuclear charge. Remember that this charge is the charge that the outermost electrons feel from the nucleus, and is usually much less than the number of protons that are felt. The effective nuclear charge does not vary as you go across a row because d electrons putting electrons in the d orbitals really do not change the amount of shielding that happens as you go from left to right across a row. You can see this by looking at a plot of ionization energy versus atomic number. You see that there are many areas of this plot that are generally pretty flat. These flat areas are areas where you hit a row of transition elements. So we don't see very many interesting trends as we go from left to right across a row. However, as we go from top to bottom down a group, we do see some pretty interesting trends. These trends are also very different from what we see for main group elements. There's one main reason why these different trends occur, and this is due for what we call lanthanide contraction. This is a phenomenon that was first observed by looking at trends in atomic radii for transition metals. The plot on the right shows the atomic radius plotted as a function of position of that element within the row of transition elements. Remember that a row of transition elements are just 10 elements across if we're just focusing on the transition elements. We can see that if we go between the first row and the second row, the atomic radius increases slightly. We do expect this because there are more electrons being added to the atom as you move to a different row. But if you go from the second row to the third row, we see that the atomic radius generally remains about the same, when we expect it to actually increase. This is the lanthanide contraction phenomenon. This occurs because when we start to enter the sixth row, we start to put electrons in the 4f orbitals. Like 3d orbitals, 4f orbitals are very inefficient at shielding the outermost electrons from the charge of the nucleus. This means that as you go from the second row to the third row, the charge on the nucleus is really not is staying about the same instead of decreasing its effect due to the addition of more electrons. This means that as we move from the fifth row to the sixth row, or from the second row to the third row of the transition elements, the atom is actually holding the electrons a bit more tightly to the nucleus than expected. This results in little to no change in the atomic radius as we move from the second row to the third row of the transition metals. Again, this trend is mainly seen in looking at atomic radii, but it has effects on other periodic properties too. For example, if we compare ionization energies for third row transition metals to those of first and second row, we see that the ionization energies for third row transition elements are generally higher than those in first and second rows. This is very different from what we see with main group elements, where the ionization energy actually decreases as you move from top to bottom down a row. Again, this is due to the lanthanide contraction. Since the atom is holding the electrons more tightly due to the higher effective nuclear charge, it's harder to ionize the electrons, the outermost electrons. Another interesting trend is looking at electronegativities, which we actually see decreasing from top to bottom down a group in main group elements. For transition elements, we see actually the opposite. If you go from the first row to the second row of transition elements, you see that the electronegativity actually increases. However, the electronegativity remains about constant between the second and third rows. Again, this is due to the inability or less of an ability for F and D electrons to shield the outermost electrons from the effects of the nucleus, resulting in slightly higher effective nuclear charges. Now that we've talked about some periodic properties of the transition metals, let's take a look at how transition metals react with other elements. Although there's lots of interesting transition metal chemistry, we're going to start with the simplest and something that we're slightly familiar with already, and that is the formation of complex ions between transition metal elements and multiple types of molecules called ligands. Transition metal elements tend to form coordination compounds. A coordination compound is basically an ionic compound in which one of the ions is a complex ion. You might remember that complex ions are ions that are formed from a Lewis acid-base interaction, where the electron pair from a molecule called a ligand is donated to a transition metal ion, which serves as the Lewis acid. We call the bonds between our ligands and our transition metal ion coordinate covalent bonds, since the electron pair only comes from one of the species. The ion on the right-hand side of the screen shows a complex ion formed between cobalt 3+ and ammonia molecules. Here, the ammonia molecules serve as the ligands, or electron pair donors, and the cobalt 3+ ion serves as the Lewis acid. The number of electron pairs that can be shared between a transition metal and its ligands is known as the coordination number. For the complex ions shown on the right, the coordination number is 6, since 6 electron pairs are shared between all the ammonia ligands and the cobalt ion. However, we know that nature does not like charge separation. Therefore, complex ions will combine with counter ions to form your coordination compound. In the example on the right, the complex ion has a 3+ charge. Therefore, we need counter ions or anions that have a total charge of -3. Here we're using 3 chloride ions. It's important to note that many of the counter ions can actually serve as ligands, and this can cause confusion as to what is part of the complex ion and what is not. Therefore, you'll notice in the chemical formula given on the right-hand side of the screen, the complex ions formula, CONH3 3+, is actually enclosed in brackets. This is a common convention to distinguish between the complex ion part of your compound and the regular ions that are part of your compound. There are many types of ligands that can form electron acceptor-donor pairs with your with the metal cation. We classify these ligands based on the number of electron pairs that can be shared at one time with the metal. This is known as the denticity or toothiness of the ligand. Basically, the toothlessness refers to the pair of electrons that are shared. The most simple type of ligand are monodentate ligands. These share only one pair of electrons at a time with the metal cation. Here's some examples of some common monodentate ligands. The one we saw on the slide, the ligand that we saw on the previous slide, NH3, which is the ammonia molecule, can serve as a monodentate ligand, where the lone pair on the nitrogen is shared with the metal cation. Although we're not going to go through naming for our unit, when ammonia acts as a ligand, we usually call it the amine ligand. When the chloride ion serves as a ligand, we call it chloro. Notice that the chloride ion has 4 pairs of electrons surrounding it. Only one of those pairs of electrons can be shared with a transition metal compound or transition metal ion at one time. Another common ligand is the cyanoligand, or Cn-. You see that there are 2 electron pairs for Cn-. Only one of those electron pairs can be shared with a transition metal ion at one time. There are many other monodentate ligands that you'll encounter in this unit. The second type of ligand we're going to look at are bidentate ligands. These are ligands that can share 2 pairs of electrons at one time with a metal cation. Here are 2 examples of bidentate ligands. This slightly more complicated molecule is called ethylene diamine. We call this the EN ligand. You can see in the molecule there are 2 lone pairs, each on nitrogen atoms. These 2 electron pairs can be shared with a metal cation at one time, due to the flexibility of the carbon chain between them. Here's an example of a complex ion that's formed between cobalt 3+ and 3 ethylene diamine ligands. You can see here that although there are only 3 EN ligands, the coordination number is still 6 because there are still 6 pairs of electrons shared between cobalt and the ligands. Another common ligand that is seen that the bidentate ligand that is seen in transition metal complexes is the oxalato ligand, or OX. This is C2O4. Here there are two pairs of electrons on the oxygens with a -1 formal charge can be shared between the ligand and the complex in the transition metal and the complex ion. Beyond bidentate ligands, you can also have ligands that share more than two electron pairs. We can collectively call those polydentate ligands. A very common polydentate ligand that you might have seen as part of your food items is EDTA. EDTA stands for ethylene diamine tetraacetado. This large ligand has 6 pairs of electrons that can be shared all at once with a metal complex ion. This forms a cage-like structure around the metal cation. The reason why EDTA is oftentimes used in food is that it helps to encapsulate metal cations, which can improve the taste of your food items. There are many different types of transition metal complexes that can have multiple types of geometries. We're going to limit ourselves to looking at only a few types of geometries. We also want to look at how we draw those types of complex ions and recognize what we're seeing. We're going to use a notation called dash-wedged notation, which we'll show you an example of in a moment. The most common types of complex ions that we will see in this unit have a coordination number of 6. You might remember that if there are 6 electron pairs around a central atom, the geometry that molecule will take is an octahedral geometry. And we see this with many of the complex ions that we'll study. In the third column, you see a Lewis structure, a geometrically realistic Lewis structure drawn of the complex ion that we saw a few slides ago, between cobalt 3+ and ammonia. In our dash wedge notation, we see that the vertical ligands, or what we'll call axial ligands, are on lines that are vertical lines that are above and below the cobalt ion. The dashed lines signify bonds that are going to be behind the plane of the slide, and the wedged lines are the ones that are coming ahead of the plane of the slide. This is a common way to show octahedral geometries in a more realistic form. Again, most of the transition metal complexes that we are going to look at are going to will be octahedral in geometry. We may also see a few complex ions that have a coordination number of 4. There are 2 main geometries that you'll see for coordination number 4 complex ions. The first is tetrahedral, which usually occurs when the transition metal is small because the angle between the angle between the electron pairs tends to be a lot larger. Another common for coordination number 4 geometry is square planar. This is very similar to the octahedral picture, except the axial positions are not occupied by bonds. Usually, complex ions that contain platinum or palladium will be square planar. Again, the most common coordination number that we're going to see for our complex ions is 6, and that's what we'll focus on. Due to the variety of ways that transition metals can bond with ligands, we see a lot of examples of isomerization and coordination compounds. An isomer, or molecules that are isomers, tend to have the same chemical formula, but different ways that the atoms are arranged in the molecules. There are two major types of isomers that we see in coordination compounds. We see structural isomers and stereoisomers. In the rest of this lecture, we'll talk mostly about structural isomers. Structural isomers are what we traditionally think of as isomers. These are molecules that have the same chemical formula, but different ways that the atoms are connected or bonded to one another. There are two major types of structural isomers seen in transition metal complex ions. The first type is what we call the coordination sphere isomers. The coordination sphere of a complex ion consists of the metal cation and the ligands that are bonded to it. Other species that are seen in coordination compounds are counterions. In a coordination sphere isomer, the ligands can actually exchange places with uncoordinated counterions. Here's a good example of a coordination sphere ion. This complex ion this coordination compound contains two halogens, bromine, and chlorine. In the first isomer, bromine is participating as a ligand, while the chloride is participating as a counterion. You can see that the bromide ion is actually bonded to the complex ion, while the chloride ion is just a counterion that helps to make the compound neutral. In the second isomer of this compound, now the chloride ion is part of the coordination sphere, while the bromide ion is a counterion. This happens very rapidly when coordination compounds are dissolved in water, where not only can counterions switch places with ligands coordinated to the complex, to the transition metal, but also water can, which results in many, many different types of coordination sphere compounds. The second type of structural isomer that's seen are linkage isomers. This occurs when different ligands connect through a different atom to the complex ion itself. There are four types of common ligands that can do this. In the next slide, we're going to see an example of the nitro ligand forming linkage isomers with a complex ion. In the Lewis structure for nitrate, the atoms in red are the different atoms that can be bonded to the complex ion. Here, both nitrogen and oxygen, the one with the formal charge, can bind to the transition metal ion in a complex ion, forming different isomers. The CN ligand that we saw on one of the previous slides is also an example of a ligand that can form linkage isomers. In the CN ligand, we can either bind with the carbon, which is the most common, or with the nitrogen. Remember that only one atom bonds at one time, not both. The last two are also common ligands, the cyanato and the thiocyanato ligands. In the cyanato ligand, the bonding can occur through the oxygen, which is most common, or the nitrogen. And for thiocyanato, we can also bond through the sulfur and the nitrogen, where binding through the sulfur is probably the most common. Now let's look at an example of a linkage isomer. For this complex ion that forms between cobalt 2 plus, ammonia, and a nitrodo ligand, there are two different isomers that we can see. These different isomers manifest themselves in slightly different colors of the compounds themselves. For the complex ion on the left, the nitro ligand bonds to the cobalt with the nitrogen atom, which yields a light orange colored solid. Where the isomer on the right has the nitro ligand bonding with an oxygen atom, which gives a darker brown color. Color is one good way to distinguish between different isomers, different structural and geometric isomers that we're going to see in the next lecture.